All right, continuing to from where we left off yesterday, we're going to continue 4.5 and do a couple more examples and realize hopefully a couple more things. So yesterday we really just dealt with rational functions that had a constant in the numerator after we reduced. So hopefully the highlights that you got out of that was when you end up with that constant in the numerator, your horizontal asymptote is pretty easy. It's going to be wherever y equals k. And your vertical asymptote is wherever the denominator equals 0. Okay? Now we're going to step this up a little bit. And we're going to move on. We're going to do example 3. And example 3 is on page 215. Okay, so looking at page 215, we are given two functions, f of x and g of x. Okay, and then f of x, you can see, ends up looking like this graph here with a removable discontinuity. Okay, and then g of x ends up looking like this graph here where we actually have an asymptote. So hopefully you're saying to yourself, well, this one must factor and x minus 3 must simplify with x minus 3 in the numerator. This one must not simplify, okay? So that's why we end up with that asymptote. All right, awesome. So let's go ahead. If I scroll down, example 3, we're going to refer to functions f and g above, and we're going to transform functions f and g to mixed number form using synthetic substitution. And I just graded some last tests, and that was a problem that was on your quiz. I'm sorry, not your test, your last quiz. And so this will be a good review over that quiz. All right, so we've got f of x is x cubed minus 5x squared plus 8x minus 6 all over x minus 3. And g of x is x cubed minus 5x squared plus 8x minus 5 all over x minus 3. All right, and we have to do synthetic division or synthetic substitution in order to write this as a mixed number or to simplify it. So if x minus 3 is actually a factor of this, then my remainder will be 0. Hopefully you know what I'm doing. If not, let me know. All right, so my remainder is 0, which means that x minus 3 is a factor. And what I'm left with then is x squared minus 2x plus 2. And I need to stipulate in this that x cannot be 3, right? Because if somebody just sees this, they're going to think, oh, that's a continuous parabola. Well, it's not, right? There's a removable discontinuity at x equals 3. Okay, now let's do the same thing with g of x. And maybe we'll divide it up like this, so that way we're dealing with two different things. All right, so g of x pretty much everything's the same except for those constants, which should tell you that x minus 3 is not going to be a factor. So I have a remainder here. So after I divide out that factor of x minus 3, I end up with okay, that's written as a mixed number. All right, so now moving on. So I think we've accomplished A, so let's look at what B is asking. Use the results from part A to explain why function f has a removable discontinuity at x equals 3, but function g has a vertical asymptote at x equals 3. Okay, and hopefully this is pretty clear to you, right? X minus 3 ended up being a factor. We had no remainder. It reduced. Okay, so it's a removable discontinuity. And then here we have a vertical asymptote asymptote because x minus 3 is still in the denominator after we simplify it. So I'll go ahead and I'll write that down for you. So here I'll kind of keep the division happening. So we got x minus 3 is a factor of numerator and denominator. I'm going to abbreviate. And reduces. So we have a removable discontinuity at x equals 3. Okay. Whereas the other one, we've got a vertical asymptote at x equals 3, since x minus 3 is still in the denominator after simplified. All right, C is asking us to make a table showing the values of f of x and g of x for all of these different inputs. And from the results, we'll describe the difference in behavior of the two functions for values of x close to 3. So we care about what's happening at 3 because we've got some discontinuities at 3. All right, so let's see. The values that I cared about, I'm just going to make an input-output table. And I'll have f of x as one of my outputs, and then I'll have g of x as another output. Now I did these on my calculator. I just created from my graphs, I just went to end a table and checked them all out so that I don't take up all your time. I would encourage you to do the same, but I'm going to go ahead and give you what the outputs were. They were 2, 4.61, 4.9601. Of course, it should be undefined at 3. Okay, at 3.01, f of x is 5.0401, then 5.41, and 10. And then for g of x, 1, negative 5.39. Whoa, negative 95.0399. That's a huge jump right there. Again, undefined at x equals 3. Now we're up to 105.0401, 15.41, and then back down to 11. So this is kind of crazy. Let's see. So I can see that on f of x, as we are approaching 3, right, if we're coming from the left, is that the left? Yeah, from the left, from the smaller side, we're approaching 5. And as we're coming from the right, the bigger side, we're also approaching 5, right? So there's just that hole, that removable discontinuity at 3. This one's really crazy. As we're approaching 3 from the smaller side, so from the left, we are going down to like negative 95, and you can bet as you get closer and closer to 3, it's going to really drop, okay? And you can get in there, you can do like 2.999, 2.99999. You can really see what's happening. Well, as I come from the bigger side or from the right, I'm getting really, really big. So that tells me that there's an asymptote, right? These two things are going in opposite directions, okay? That tells me that there's an asymptote there. All right, so we'll say f of x stays close to 5. As x goes to 3 from left and right. Oops. I guess I can get rid of my calculator. And g of x gets very large in both the negative and positive direction. So as x goes to 3, oh, I shouldn't say so as x goes to 3, from left and right. Okay. Moving on to D. Find the exact coordinates of the removable discontinuity in function f. Well, basically what I'm looking for is what should the value be of this thing when x equals 3? What should it be? Okay, so really all I'm going to do is I'm going to plug in 3 into my simplified version. Okay, let me show you. So I'm going to plug 3 into this. Now I know that it can't actually exist, but I can see from this graph that it's approaching from both the left and the right. It's approaching some output. And if I plug 3 in, I'll figure out what that output would be. Okay? So I'm going to plug 3 in to my simplified version of f of x. Actually, let me call this f of 3. So we're not confused, even though really this isn't correct because you can't have 3, but so maybe I'll change my mind. Let's call it y. But let's say that this is function f at x equals 3. Just, I don't know. So that way you have some notes on that. So you know what the heck it is that we're doing here. So I got 9 minus 6 plus 2, which is going to give me 5. Okay, so however, let's just stipulate that f of 3 cannot actually equal 5 since f is undefined at x equals 3. Okay, so we have a removable discontinuity at 3, 5. Okay, I'm going to do one more example. Example 4, which is on page 217. And this is really an example where we're going to end up with numerator and the denominator, the polynomials in those are of equal degree. Okay, so if you look back to your parent graphs, what we said here was if I had a linear over a linear, or it could be a squared over squared, anything like that, we were going to find our vertical asymptote, again, wherever the denominator equals 0. But our horizontal asymptote were basically going to be the coefficients of the leading terms. That was going to give us our horizontal asymptote. So we need to keep that in mind, and I'll write this down again as I make notes on it. So going on to example 4, let's see what we got here. Oh, I think that's still example 3. Okay, example 4. So we're going to plot the graph of the rational function f of x showing any discontinuities and stating which kind they are. Okay, so there it is. And we'll describe the end behavior, the behavior when x is far away from 0, and explain how this behavior is related to the coefficients in the rational expression. All right. Writing down the problem. F of x is 3x squared minus 25x minus 50, and x squared minus 16x plus 60. Okay, this looks to me like it can be factored. So when I factor this, let's see, I end up with 3x plus 5 times x minus 10, and x minus 6 times x minus 10. Ooh, looky there. So I got some factors that reduce. Okay, and so when I reduce this, I end up with 3x plus 5 over x minus 6, given the fact that x should not equal 10, or cannot equal 10. Okay, so that tells me that I have a removable discontinuity at x equals 10. It also tells me that I have a vertical asymptote at x equals 6, right? Wherever the denominator is equal to 0. Let's do this instead. Not since. Let's say vertical asymptote at x equals 6. The way I got this was I set denominator equal to 0. Okay? So that's always going to be the case for your vertical asymptote. Okay. Now, there's some other stuff happening here. So let's talk about our end behavior. Okay? So I think what I'm going to do is I'm going to think about this graphically, and I'm going to think about inputs and outputs, okay? Let me go ahead and graph this. So I know I have a vertical asymptote at 6. Let's just call 6 right here. And I know that 10, I've got a discontinuity, a removable discontinuity. And at 10, I've got some removable discontinuity. So let me see what this thing is when x equals 10. So I can go right back up here, figure out where that removable discontinuity is by plugging 10 in. So when I plug 10 in, let's see, 3 times 10 plus 5 over 10 minus 6, I get 35 over 4. Let's see, what is that? Not quite 9, 8 3/4. Okay, so I know that my removable discontinuity is somewhere up at like 8 3/4. Oh, let's do 1, 2, 3, 4. So it's up here somewhere. Maybe I'll go by 2's on this. 2, 4. So it's about here. Okay. Now let's think about the end behavior. So I'm going to do an input-output chart for that. So what happens as x gets really, really large, and what happens as it gets really, really small, or large in both directions, both positive and negative directions. So let's try, how about 100, 1,000, so that's going in the positive direction, and then how about negative 100, negative 1,000. Well, when I plug those numbers in, if you look at this, you're going to get approximately 3 for all of these. Okay? So you can put this into like your graphing calculator and you can try it that way, or you can just manually plug it into the function. So if you decide to manually plug it into the function, let's just bring your attention down here. As these x's get really, really big in both the positive and negative directions, what I want you to think about is that the 5 and the negative 6, they don't really matter anymore. So if I plug in 100 for x, I'm going to have 300 over 100, so that's 3. If I plug in 1,000 for x, I'm going to have 3,000 over 1,000, so that's 3, approximately, right? Because there would be this little teeny bit of change right there. Okay, so basically you get 3. So as I get really, really large, this thing is approaching 3. And as I get really, really small, this thing is also approaching 3. Okay, so let's talk about end behavior. So I'll say, as x goes to infinity, f of x goes to 3. And as x goes to negative infinity, f of x also goes to 3. So what that's telling me is that I have a horizontal asymptote at y equals 3. Now, what's another way that I can figure that out algebraically? So I'm going to take you right back to your parent graphs there. Horizontal asymptote is always at those coefficients of your leading terms. Well, what are my leading terms here? My leading terms are 3x and x. So it's 3 over 1, right? So the horizontal asymptote is at y equals 3 over 1, which is 3. Okay? So that's another way of figuring that out. So I know that I've got a horizontal asymptote again, when I plugged in 10, I was up here, so I know that I'm up in this quadrant here. It's going to look something like that, and you can get on your graphing calculator and get a more exact graph. And then, so that means that on this other side, it's going to be coming down something like this. So we might want to put a little note here that horizontal asymptote is at, let's see. If I have, how can I, sorry, I haven't thought this through very well. I know, we'll say it's the quotient of coefficients of leading terms. How about that? And you might want to highlight that